All right, so welcome back. So last time we went over nucleophilic aromatic substitution. So this is the nomenclature, the shorthand notation for nuclear. So N for nucleophilic, substitution aromatic. I don't quite know why the letters are all in that order, but SNAR, nucleophilic aromatic substitution, right? And we went over the fact that in order for this to happen, you need a strong electron withdrawing group and a leaving group ortho or para to the leaving group here. So we see that there's no reaction when I try to do a nucleophilic aromatic substitution on this. Um, and when I take the molecule and I heat it, it looks like you're doing a nucleophilic aromatic substitution. But are you really doing a nucleophilic aromatic substitution? Let's see. So what we find is if I take chlorobenzene and I heat the living bejesus out of it with sodium hydroxide, which is a good nucleophile, but not a great nucleophile, that you get a substitution reaction happening. And the question is this a nucleophilic aromatic substitution reaction? Well, to get some answers, let's take that reaction and instead of using sodium hydroxide, let's use a reagent that's a stronger nucleophile slash base. Let's use sodium amide. So when I take sodium amide, I find that I don't need to really heat this reaction a lot to get this reaction to go. In fact, it works pretty well. And if I take this, again, this looks like a nucleophilic aromatic substitution. But am I really doing a nucleophilic aromatic substitution? To see if I'm doing a nucleophilic aromatic substitution, let's add a second group on there. Now, if I was really doing a nucleophilic aromatic substitution, this would be the only product that I make. But because I make a mixture of both of these products, what this tells me is that the mechanism by which this goes by is not nucleophilic aromatic substitution. Like the NH2 minus is not attacking here, making that Meisenheimer complex, which then kicks this out. And that makes sense. This is actually an activator, right? This is not an electron withdrawing group. That if I do a nucleophilic aromatic substitution, I attack here, I make that Meisenheimer complex, that thing is not going to be stabilized by an electron donating group. So it makes sense that I'm not doing a nucleophilic aromatic substitution. So what's happening here? What's thought to happen here, and again, you see the same thing if you use an isotopically labeled substrate. So this is where you take this and you label this carbon C13. If I label this carbon as C13, then you see you get a 50-50 mixture of where the NH2 is added to the C13 carbon, and then the rest is where the nitro group is added to a neighboring carbon here. So what's happening here? Well, what's thought to happen is that what you do is we make what's called a benzyne intermediate. So this is a strong base. And so what's thought to happen as a first step is you eliminate this proton to make a triple bond between this molecule. Very, very, very interesting looking, right? And we'll go over why we think the evidence for making the benzyne. So what's thought to happen is this strong base removes this proton here, making this carbanion, which then causes this chloride to leave, the leaving group to leave. You make what we call benzyne, the I and E, the Y and E coming from the triple bond. Once you make the triple bond, what's then thought to happen is this isn't super stable. So what's going to happen here is that another molecule of NH2 minus is going to attack this carbon, kick the electrons here to make the anion. This carbanion is very basic. It's basic enough to remove the proton off ammonia, and bing, bang, boom, you've gotten your substituted aromatic ring. And again, because I can attack either because I can either attack the C13 carbon or the C12 carbon, you see where you get the scrambling of the products here. So we call this an elimination addition mechanism. So I eliminate the chloride to make benzyne, and then I add my nucleophile to make my new product. So this is the overall mechanism drawn for the OH minus. So I do the proton transfer. That gives me my carbanion. I have my leaving group, which is helped by the carbanion kicking down to make benzyne. I have nucleophilic attack to make another carbanion, which then deprotonates whatever conjugate acid of your base to give you the final product here. And the evidence for benzyne is the fact that if I take this reaction, if I take this NH2 minus here, if I take the NH2 minus and I couple it by reacting it with a diene I get the Diels-Alder reaction, right? You start to see a very small amount of the Diels-Alder product forming. Because you're making the Diels-Alder product, that Diels-Alder product is presumably coming from this triple bond doing the cycloaddition with this diene to give you the Diels-Alder product. So at this point, we have three different types of reactions we can do with an aromatic ring. We can either do an electrophilic aromatic substitution, a nucleophilic aromatic substitution, or an elimination addition reaction. So what you want to do is when you see an aromatic ring, to distinguish between these three reactions, you want to ask yourself, are the reagents being used to modify the aromatic ring, are they electrophilic or nucleophilic? So if they're electrophilic, things like bromine, nitric acid, sulfuric acid, alkyl halides, acyl chlorides, those are all electrophilic reagents, then you're doing an electrophilic aromatic substitution. If the reagents are nucleophilic, then what you want to do is you want to say, are the three criteria satisfied for nucleophilic aromatic substitution? Strong electron withdrawing group, leaving group, ortho-para to the strong electron withdrawing group. If the answers to all of those things are yes, you're nucleophilic aromatic substitution. If the answers to any of those things are no, then your elimination addition reaction. So this is just a review of all the different reactions that we've gone over so far. Bromination, chlorination, nitration, sulfonation, alkylation, acylation. I can reduce the nitro group. I can, and we can remove the sulfonation group. Like, so I can go from here and then remove it to go back to the benzene ring. I can halogenate the benzylic position of an alkyl halide. I can oxidize the benzylic position of an alkyl group on a benzene ring. I can reduce the ketone, the benzylic carbonyl of a ketone of a benzene ring. You can also do nucleophilic aromatic substitutions. We can also do elimination addition reactions to get to different products. All right, so I hope that's the end of chapter 18. Let me know if you have any questions. That's a lot of different reactions that we added on there. Make sure that you can incorporate all of those reactions into the forward synthesis, right? You can come up with those forward products. This involves looking at the reagents. So if we go back here, right? This involves looking at the reagents and determining if the reagents are nucleophilic and electrophilic. And then that kind of dictates the mechanism, the type of reaction that you're going by. And remember, what we're doing is, some of you might be doing more straight memorization, which is okay, but what I'd like you to do, even if you're doing straight memorization, is to try to use the mechanism to solidify that memorization. All right, thanks. Let me know if you have any questions, and have a great day.